This is where we start. We should
Okay.
start.
So tell me, what are going to be your equations?
My equation is going to be zinc solid.
Okay. Zinc solid.
Plus copper, that's Cu. Then NO3 in bracket.
Okay.
And 2 there, right? Okay. Then that will be aqueous.
Okay.
Then the product is going to be zinc, zinc nitrate in brackets, nitrates in brackets.
Okay.
That's NO3 in brackets, then 2.
Okay. And that's going to be AQ.
Yes, AQ, yeah. Plus copper. Are you writing, Doc? I can't see your writing.
You can't see my writing?
Oh, I know why. This is blocking it.
Okay.
Yes. Then,
okay. Do you see it?
Yes, I can see it.
Okay.
We have 1, 1, 1, 1. Equation is balanced.
Okay. So then what do I do next?
The next thing we have to look for a total, is it ionic equation?
Okay. Yep. Total ionic equation.
Ionic equation. So which is going to be zinc solid,
Okay.
plus copper 2, that is a superscript 2 plus I'm sorry, aqueous.
Okay.
I think plus nitrates, iron, NO3 negative. Okay.
How many?
Sorry, I said.
You said 2?
No. What did I say? I said what's it called now? Nitrate 3.
Okay.
It's going to be aqueous too.
Okay. How many of them am I going to have?
You're going to have 2. 2 is going to be right there. Yes.
Okay.
Then on the product side, we're going to have zinc. I think that one should be aqueous though, right? Though, since
That's right.
Since it's mixed with something else.
So zinc.
Zinc 2 plus.
Okay.
Plus 2 nitrates.
Okay.
Plus copper negative there, then plus copper solid.
Okay.
Aqueous, yes. Copper solid. So we're looking for spectators now, right?
Okay.
That's They call it nets ionic equation.
Yep. So who are spectators?
So let me look. Nitrates. What else? I think that's it.
Okay.
So we're gonna have the net as in zinc solid plus copper 2 plus aqueous. And on the product side, you're going to have zinc 2 plus aqueous. Then plus copper solid.
Okay. Now, who's going to be oxidized and who's going to be reduced?
The one that gained is oxidized, which is gain. When you gain, that means you don't have that plus. Yes, this is going to be oxidized. This zinc. Let me take this thing off.
That's right. Zinc is going to be oxidized. That's right.
Yes. Okay. Then the other zinc is going to be reduced.
No, so it's going from 0 to +2, so that's oxidized.
Oxidized.
Okay. And then that means copper is going to be reduced, right? Because you're going from...
Yes. Copper is going to be reduced.
Okay.
Because we're going from plus to 0.
That's right. Okay, piece of cake?
Piece of cake.
Good. Okay. So we just did that. Okay, so activity series. Okay, so the way the activity series works is there is a hierarchy in terms of the metal, in terms of replacement, right? So we just did zinc. Let's see.
Zinc and copper. Let's
Zinc
see.
and copper. Okay.
Oh, zinc is higher than.
Exactly. So since zinc was higher than copper, we can take zinc metal and it'll be able to replace the copper. Okay. In a solution, right? Sorry, I'm eating my lunch finally. Been a long day. So
that's what this thing means.
Yep. Exactly, that's what it means. So yeah, there's a hierarchy. So anytime that you have a metal, when it's a metal, it can replace any of the metals below it in a solution. Okay. So if I have, let's say I have zinc plus silver nitrate, AgNO3. So do you expect a reaction to occur? And if so, what are going to be your products?
Hold on, Doc. Please let me think.
Okay.
Where's okay. I think it's going to be zinc nitrate.
Okay.
Because zinc is higher than I don't know. That's what that means.
Yep.
I saw it. I printed it out from what you gave us. I said, "What's activities?"
That's what it means. And so then you're going to be left with silver, salt. Okay. Okay. So let's say we have, we're going to go SN plus BaNO3. Barium nitrate. Okay. What's going to happen? Or is anything going to happen?
SN, where's SN? SN is right there, and Ba is up there. I think no reaction will happen, right, Doc?
That's right. NR.
Because SN cannot replace BA because BA is higher than its inactivity zero.
That's right. Okay, so let me explain this just a little bit a little more detail here. See, now that you got that. Okay, so all of these guys that are in this square here, all of those guys can replace hydrogen in water, in steam, or in an acid. Okay, all of these guys can do that, right? All of these guys can replace hydrogen if it's steam and an acid. All of these guys can replace hydrogen if it's an acid.
If it's an acid.
That's right. And all of these guys are below hydrogen, so it can't replace hydrogen. So these won't replace it. Okay? So if I have, let's see. Let's say we have HCl aqueous plus BA solid. What's going to happen?
Okay. I have hydrogen. It's going to be, since BA can replace hydrogen, or so that means we're going to have hold on, Doc, please let me think. I think H is going to be just by itself.
That's right. So
and we're going to have barium chloride.
Okay.
Right?
Yep, that's right.
Thank God.
And of course, you'd balance it. That's AQ. Okay, so we need 2 of these.
2 of that and 2 of the other side. Right there.
It's right here.
Oh, 2 is there already. Sorry.
Okay. Piece of cake.
Piece of cake.
Okay.
I understand how this thing works now.
Yeah. Okay, what about this?
Magnesium liquid. Magnesium is will replace hydrogen from steam of acid. So in this case, we can have magnesium oxide.
Are we going to have magnesium oxide?
Hold on, Doc.
What does the table say?
Oh, sorry, let me see. The table, we have magnesium. Where are you? Magnesium is higher than, magnesium can replace hydrogen.
When?
It can replace when, where is it? We replace hydrogen from a steam of acid.
Okay.
So this is not acid.
And it's not steam, right?
It's not steam.
That's right. So no reaction. I did that earlier today. Okay. So what if I go?
No reaction.
H2O S.
We have chromium. Where is it here? Okay, right there. We'll replace hydrogen from steam. But doctor, please, how do you know if it's steam? From steam or acid? I know when I see acid.
That should be gas. There you go. Because water, steam is gas, right?
Yes, because
So
it's
that's how
going
you
to
know.
produce steam.
Yep.
So that's gas, right?
That's right.
Okay. So that means we can have H by itself while we have
So then we're going to have H2, right? Because it's a gas. Okay.
Then chromium oxide.
Piece of cake.
I'm going to write it down, Doc. I don't want to forget it. But I'll remember that because of the table.
Yep.
So whenever I see gas, because it's going to produce steam, so I know for sure. Then whenever I see acid, then I'll be able to tell.
Okay.
Okay. And we're allowed to use the table, right? During the exam. Okay.
And okay. So let me clear. Okay. So another form of oxidation is oxidation of organic material. Now, when we do oxidation of organic material, all we're doing is adding oxygen. Oxygen is as our oxidizing reagent. Okay. And so it's just basically a combustion reaction. That's all it is. Okay. So write the complete burning of ethane.
Okay. It's gonna be ethane, C2H6 plus oxygen.
Let's see. C2H6
plus oxygen, which is going to produce carbon dioxide and water.
Okay.
I think you said it before, though.
Yeah. Yes, you did. We've done this a lot.
Yes. That one is going to be gas. Gas. And oxygen is gas.
Okay.
They're not balanced, though, right?
Okay. Right, they're not balanced.
Carbon is 2 on the reactant side.
Okay.
And we have only one carbon here, so 2 is going to go there.
Okay.
Now, then our H, hydrogen, we have 6 on the reactant side, so we're going to have 3 right there.
Okay.
Then let me see. Then on this side, I have how many? This is 3 oxygen, 3 plus 4, that's 7, right? Oh?
Yep.
7. So if you have 7 here, then that means it's going to be 7 here. On the test, I forgot to do this though. On the last exam, I forgot to do this.
I know.
Oh.
And then you do what?
I left it because I don't want to cheat. The time was up, so I scanned it like that.
Yeah.
So, we're going to use 2 to multiply the whole thing.
That's right.
So that we don't multiply the other side. We don't multiply, that's 3.
Oops, I forgot it. I forgot to do that. Sorry, my bad. My head is in 50 different places. I have to make an adjustment. I just realized I need to make an adjustment to your exam. Okay.
Yes, yes. If I see this in the exam, I don't know. This one is easy.
Yeah. Okay, so when you have a double replacement reaction, you can sit there and set up so that you can determine what is going to be your precipitant. So usually you have a precipitant that's forming, and then, yeah, okay. So the way that you would do that is, do this.
Solubility.
Went too far. Okay, so if I have, let's say we have NH4, ammonium acetate. Oops. I was going to write it out. Ammonium
yes,
acetate.
I know. Ammonium acetate is not C2H3, right?
Yeah. O.
And O.
2.
2.
Plus barium. I mean, not barium. I'm not thinking today.
You're tired, though. I don't know how you do it. I don't know how you do it.
And today was a long day. I've been up since 4 this morning.
Oh, no. I will be sleepy. I won't know what I'm talking about.
Aluminum bromide. Okay, so the way that we determine that both of these are aqueous is by looking
their solubility.
Yep. If it says soluble, it's aqueous. If it doesn't say soluble, if it says slightly soluble, anything in pink is going to be unsoluble. It's going to be a precipitant. Okay. So if we go that, now a double replacement reaction, what are we going to get on the other side?
So barium is, let me see, with carbonate is not, I have acetate. Acetate is here. So barium, hold on, though, please let me think.
Okay. So we have ammonium acetate reacting with aluminum bromide.
Then we have ammonium. Where's ammonium here? I'm looking for ammonium. Oh, right here. Ammonium and barium. I mean, bromide right now. Yeah, ammonium and bromide can go together.
Okay. So.
And
H4. Br. Okay.
Then barium and acetate.
You mean aluminum?
Oh, sorry. And let me say, I didn't check that though before I say, where's aluminum?
Aluminum? Al.
Yes, I see it now.
Yeah.
No, they're slightly, they're not, this is slightly soluble.
Okay, which means that it'll form a precipitant. So we'll write it down.
Oh, we still write it, but we won't separate it.
That's right. Yeah. So, but then we'll say it's a solid, right?
Solid. That's right.
So let me shift everything a little bit so we can get it on the screen. So much faster with one person.
And
oh my gosh.
And doctor is so easy with only me.
Yes, it is. Oops. That's a 302. And there's 3 of them. Okay, so then we put an S here. Okay, and then that would be AQ. Okay, you see how that table works?
I see it.
Okay, good.
I see it. So this will be so useful when one is doing ionic equation. When one is separating what's it called now? When one is doing the total ionic equation. You understand what I mean, Doc? When
Yep.
So one will be able to tell which one you should separate, which one you're not supposed to separate.
That's right. Yep. Anything in pink can't be separated. Or I can't tell if that's pink or orange on your screen. On my screen, it's pink.
It's pink. It's pink on your screen. Yeah. Even the one I printed out, the one you gave us is pink too.
Okay.
We're allowed to use it though, right, Doc?
Yep, that's right. Yep. Okay. Piece of cake?
Piece of cake.
Good, good. Okay. And this is just, it explains all the solubility and how is it.
Okay.
Okay, so we have solutions of lead-2 nitrate and sodium bromide are combined. Write the net ionic equation.
Of lead nitrate and sodium bromide. So it's going to be PB.
Okay.
PB, the nitrate in the brackets. 2, since it's lead 2.
Okay.
And it's going to be aqueous.
Okay.
Plus sodium bromide, which is going to be Na, Br. Sodium is just, let me see. Sodium is just +1. Bromide is, I think it's +1, so let me plus. I mean negative. Yep, negative. Okay. Combined, write the net equation of, okay. Now it's going to produce lead bromide. Doc, are you there?
I'm here.
It's going to be PB.
Okay.
Br 2 because of lead 2 plus here, that's where we need that thing.
That's right. So what is it? Aqueous or solid?
I think it's, let me quickly check though. It should be solid though.
Okay.
Should be. Barium and yes, it's solid.
Okay.
Then it's going to give us sodium nitrate.
Okay.
Which is N. And that one is going to be aqueous.
Okay, that's correct. Okay, is it balanced?
Let me see. We have one iron. We have one. We have oh, 4 minute, Doc. I want to see what's going on. Oh, yeah. No, it's not.
Okay. So what do I need to do to balance?
We have two nitrates here. So we need two nitrates right here.
Okay. Two nitrates. Right here.
Yes, right there.
Okay.
Then what else is there? This is two bromide. Then yes, we need two bromide here. That will number Na.
Okay, so for our net ionic equation, our total ionic equation.
Okay, so we're going to have lead by itself.
Okay.
Then since it's two, we're going to put the 2 plus.
Okay.
Aqueous. Plus 2 nitrates. Yes, negative. Then plus 2 sodium. Sodium is the plus, just plus. Then bromide. Bromide, which is two. We need two of that too.
Okay. There you go.
Aqueous. Then yes, aqueous too.
Okay.
Then on the product side, we're going to have PB and BR to solid plus 2 sodium and 2 nitrates. Aqueous. 2 nitrates. Aqueous. So we look for her spectators. Nitrates.
Anything else?
Yes. Sodium.
So then we're left with just.
We left with just lead 2 aqueous plus bromide, 2 bromide aqueous. Then product side. Yes, we forgot that. We're gonna have lead bromide. To solid.
Okay. Yes, no, maybe?
Yes.
Okay.
No, maybe.
Okay. Okay. So neutralization is just a special case of exactly the same thing that we're doing. Only thing you're going to end up with water, right? Or a weak acid.
So that one has to do with acid.
Yep, that's right. Let's see. So, okay. So here, if we have HCl reacting with sodium hydroxide,
Sodium hydroxide.
And what are we going to make?
We should be making HOH. Is it hydrogen oxide? Is that correct, though?
HOH, which is the same thing as
water. Oh, that's true. That's true.
Yes.
That's true. That's true.
Okay.
2H. Okay. Plus
and that solid,
sodium,
liquid, or gas.
Oh, sorry. It's going to be liquid.
That's right.
Oh. Then sodium chloride. Aqueous.
And you already know how to break it down, right?
Huh? If I know.
You already know how to break it down, right?
You mean the way we did it the other ones?
Yes.
Yes.
Okay.
This one, we can break these ones down because there's no any solid.
That's right. Except for water. Water you can't break down.
Yes, you can't break water down. No.
Yeah. Okay. So. Okay, so your net ionic equation would be this. And here's your arrow. I forgot the arrow. Jeez. Old age. Or actually, it looks like my arrow moved.
Yes, it's actually it's an in between eliminate and eliminate.
Yeah, you fix that. I don't know what happened. Okay. Okay, so this is just another example. You can go through the same process, right? The only thing that's different here, right, is, let me go clear. We have sodium, right? If we go Na, I'm going to write this one out for us. CO.
Solution of sodium carbonate. Yes.
Na2CO3, aqueous,
plus HCl, hydrochloric acid.
It's going to yield.
It's going to yield sodium chloride.
And?
This is double there plus carbon dioxide, right? And water.
That's right. Because it's going to decompose. So yes.
Yeah, decompose, yes.
That's right. So it decomposes to carbon dioxide and water. So H2O
Okay, that's where the oxygen will break off now.
That's right.
I think you taught us this too.
Mm-hmm. So because you get this initially, right? You get H2 CO3, and then that just decomposes into H2O
H2 and
and CO2.
CO2.
Okay.
Yes. The H2 borrowed one oxygen from the.
That's right. Okay. So then that's. Okay. So this happens. This happens with a couple of things, right? Let's see. Hold on. Come on. Okay, not what I wanted. Not what I wanted. Come on. So that's just another example. So this is an example where there's no reaction because you don't have a precipitant forming. Okay. What did I missed one? Hold on. I think I went too far. I skipped something. What did I skip? Not this one. This one, yeah. I did skip it. So clear. So this happens when you're combining that your H's and to form carbonic acid. It's unstable. So when it's coming in that form, it's being combined by being made by something else. It's going to be unstable. It's always going to go to carbon dioxide. This is the same thing. Only thing, this should be a gas as well too. So that should be sulfur oxide, sulfur dioxide, and then here this is going to form ammonia. Okay, piece of cake.
So this arrow shows that it's still forming, or this this is arrow and arrow. So that one is what I'm trying to.
It's an intermediate. So, but it's so quick that you don't even notice it. So this middle one, it's so quick, it doesn't last long. It dissolves into this. It breaks down to that. Okay. Okay. Let's see. Trying to get it set up so that we have a few more people that'll be coming in a little bit later, and I'm thinking I'm going to try to text them to see if I can get them early. We're early, sort of. Okay, so this is just another example. You kind of got this down, so you don't need to go over it again. Okay, so
summary of
summary of everything.
Okay.
Okay. Questions, concerns, Cash?
No question.
Okay, so I have of the class for me. I'm like group projects.
Get to laugh at us.
Exactly.
See our videos.
Yeah. Okay. Can you guys see my screen?
Yeah.
Screwed up. Okay, so we're going to go over this pretty fast. Slow me down if you need me to slow down, but we're going to try to get through it so I can get some sleep tonight, and you guys can get some sleep tonight, and I can at some point finish grading. Okay, so let me tell you about some characteristics of gases. So gases are compressible, they're expandable. So they have low densities, they could at low volumes or low quantities, they could actually mix fairly well without interacting. And then, and if they're inert, you can sit there and mix them regardless. And they exert a constant pressure on all of the walls of a container uniformly. Okay, so compressible, expandable, right? So if you push them in, you can sit there and compress them into smaller things, so we can get these nice cylinders of gases and stuff that we can use later on and blow up balloons and, get a little high, get the giggles or sound like Mickey Mouse, They're expandable. So if you sit there and let them go, they can actually cause things to expand further if there's anything keeping them in check. Gases have low density, so they kind of float on water. So we talked about bodies earlier, right? So why do you float if you take a big, deep breath and you're laying on top of the water? Why are you floating?
Is it because you have all the gases in your lungs?
Because all the gas in your lungs, right? So if you had filled yourself up with water, what are you going to do?
You're gonna.
Or if you breathe out all of the air, you blow it all out, you're going to sink, right? So why does a dead body, float? So if we kill somebody, throw them in the river, why do they always come up and float? In the beginning, they sink, but why do they start floating? Are you there, Nadia? And Nadia?
Doesn't your body naturally release gases after you die?
Yeah, they do, because your body starts to decompose, right? So because your body's decomposing, the bacteria is actually producing carbon dioxide, and so you start to float.
Was that going to be on the final?
Maybe. I'm going to say, what do you need to do to keep a body from? So if you kill somebody and throw it in the ocean, and you don't want anyone to find out, what do you need to do? Okay. Come on. Okay, so if we're mixing gases, we can sit there and have a container where we have two different gases that are in the same container. So if the gases are in such a low quantity, they won't ever, or they will rarely find each other, right? If we increase that quantity, we increase the possibility of them finding each other. But we can mix gases within the same container, and then if the gases are inert, they can sit there and exist in the same container, not truly affecting each other under ideal circumstances. Okay, and I'll kind of have to explain that a little bit later. Okay, so the last thing is that gases are going to be able to exert pressure in a uniform manner on all of the courses. Where like a liquid, where's a liquid? A liquid, okay? So here, the liquid is only occupying this space, that's it. It's gonna only exert pressure the depth of the liquid. The gas is gonna be able to exert pressure on all uniform walls. You guys kind of get that? Okay, so the kinetic molecular theory. Okay, what is kinesiology? Does anybody know what kinesiology is?
It's like the physical therapist stuff.
It's the physical therapist stuff. Anyone? No one knows what kinesiology? Kines, that word kinetic or kinetic, what does it mean? Now, this doesn't mean that you guys get to be silent.
Is it movement though?
It's movement, that's right. It's movement, okay? So kinetic, molecular, so the movement of molecules. Theory. So in other words, we're saying that molecules are moving. And then since molecules are moving, as gas, as we increase temperature, gases are going to move faster, right? And that's pretty much the take-home message. So in terms of kinetic energy, the kinetic energy is going to be directly proportional to the temperature. Well, also the kinetic, pressure is also going to be directly proportional to the temperature. Okay, so under ideal circumstances, under perfect conditions, the fact that a molecule bounces off a wall, you're not going to lose any of that kinetic energy under perfect conditions. Reality, that isn't the case, but that's the assumption that we're making, right? So that's part of our assumption. as well. Okay, so, and in terms of space, you know, gases, although they occupy a volume, as if they don't take up any space, or it seems as if they don't take up any space. Okay, so pressure is just force over area. So it's essentially the amount of force that's over a given area that we're looking at. Okay, now factors that affect pressure is volume, quantity, or amount of gas, and temperature. So we have volume, number of moles, and temp. Okay, so if you guys go out on the beach on a cool day and you're walking in the sand with no shoes on, right? Are you guys walking fast or slow or just moderately? You know, you're out there with your boo and everything like that. You're trying to woo her and everything. Oh, isn't the water beautiful? And look at the sunset and all of that. Are you guys speed walking?
No.
No. Okay.
No.
So on days where it's like 200 degrees outside or something like that. Now, and you're also barefoot. Are you going to be walking to get into the water, or are you going to be racing to get into the water?
You're not running to the water.
Okay.
You'll turn into Usain Bolt.
Exactly. So you're going to be in a hurry to get into water because temperature has increased. So the molecules are going to be just like you. So as the temperature increases, those molecules are going to be moving fast. Okay. So let's see. So this is a mercury barometer. Barometer measures pressure. And in this case, we're looking at atmospheric pressure. Atmospheric pressure is the pressure that's exerted by just the atmosphere itself. At sea level, the atmospheric pressure is going to be equivalent to 760 millimeters of mercury. In other words, in a column, in a vacuumed column, the mercury will rise up 760 millimeters because of the pressure that it's put on. Okay, so that is considered to be the atmospheric pressure. So we can say 1 atmosphere, 1 ATM, which is what we refer to an atmosphere, is going to equal to 760 millimeters of mercury. Okay. So, and an atmosphere is a unit of measurement for pressure, and millimeters of mercury is also a unit of measurement for pressure. Okay, so properties of gases are going to be pressure, volume, amount, and temperature. Okay, and you know what all that they are. So you know what pressure is just force over area. Volume is just a three-dimensional space that's being occupied by the gas. Amount is just the number of moles or quantity. And temperature just going to represent the average kinetic energy of the gas. Okay, and so the relationship between between each of these items and pressure, volume is indirectly proportional to pressure. The quantity is directly proportional to pressure, and the temperature is directly proportional to pressure. Now, you guys remember at the very beginning of the class, we talked about directly proportional. Directly proportional means that as one thing that you're looking at goes up, the other thing is also going to go up. So as temperature goes up, pressure goes up. As the amount that you pack into a bottle goes up, the more pressure you're going to get. As the amount of pressure goes up, the volume goes down. Right? Okay, and that makes sense, right? Okay, so units of pressure, the atmosphere, and we already talked about 1 atmosphere is equal to 760 millimeters of mercury. The torr, 1 atmosphere is equal to 760 torrs, which is also equal to 760 millimeters of mercury. 1 atmosphere is equal to 101,325 pascals, or we could say 101.325 kilopascals. Okay. And the Pascal is SI units. So that's the one that's normally used in science. But you know how we do in the US. Screw science. We like pounds per square inch. So we need the conversion for that as well too. So 1 atmosphere is equal to 14.70 pounds per square inch. 1 atmosphere is equal to 29.92 inches of mercury. And 1 bar, which is approximately equal to 1 atmosphere. 1 bar is equal to 100,000 pascals, or 100 kilopascals. Okay, are you with me? Are you with me, Brian?
Kind of trying to follow along.
Okay, so if we're doing pressure measurements, one of the devices that we would use in the lab is called an open-ended manometer. So an open-ended manometer is actually attached to a vessel that's holding the gas that we're interested in measuring. It is a column that has mercury in it, and it's like a U-linked column, and I'll show you what that looks like here in a second. And so, as if the gas in the container is greater than the atmospheric pressure, it's going to actually push the gas out. And let me just show you what it looks like, and then we'll go to what gauge pressure is and then what absolute pressure is. Okay, so this is a manometer, open-ended manometer. This part is open to the atmosphere, so it's an open vessel. And then this one is actually attached, this part is actually attached to, in this case, the flask. So the gas in here is going to be pushing the mercury that's in this column to the other side, right? So the height difference as it pushes the mercury up, is going to be used to determine the pressure of the gas itself. So we know that atmospheric pressure is 1 atmosphere, which is how many millimeters of mercury?
760.
And let's say that this was 65 millimeters, that it changed in height. So then my total pressure, or my gauge pressure, is going to be the sum of both of these. So then that's going to be 825 millimeters of mercury. And then that's going to represent, we call it gauge pressure, or the pressure, the total pressure in the flask itself. So that tells you the pressure of the gas that's in the flask. I'm sorry, and this isn't gauge pressure. This is absolute pressure. P absolute. Okay, so in this case, let's say we have the same distance, it goes up 65 millimeters of mercury, but it's going up towards the gas itself. That means that the pressure, the atmospheric pressure, is greater than the pressure on the inside. So in that case, we're going to use that 760 millimeters of mercury. And then we're going to subtract 65. Okay, so then in that case, that's going to give me a pressure that is going to be less than an atmosphere, which makes sense. So the pressure in here is going to be less than an atmosphere, which is going to be, what's that, 695?
Yeah.
Okay. Questions, concerns, Cash?
What's the symbol for absolute pressure?
It's P absolute. P, that's P absolute.
Oh, okay.
ABS.
Doctor, please, I do not understand it.
You don't understand?
Yes, I do not.
Okay, so if we look here, right? So the pressure here in the atmosphere is going to be pushing the mercury up, right? And since it's pushing the mercury up, then, okay, let's start off with this. So if we disconnected this whole thing, right, what would happen is that the mercury would be at even levels. So you'd have a mercury here and you'd have mercury here. It'd be even with each other, right? So as soon as we connect it to, let's say we're doing a chemical reaction, and that chemical reaction makes gas. Well, we can calculate the gas by playing with by connecting it to an open-ended manometer. Well, the open-ended manometer relies on atmospheric pressure. So if the atmospheric pressure is greater than the gas that's being generated in the flask, what's going to happen is the mercury gets pushed down, right, by the atmosphere. So the atmosphere is pushing the mercury down. And do you see that gray? That gray represents the rise.
The mercury.
Okay, so then if you subtract this volume here and this volume, this distance here and this distance, and usually you have a metric scale, millimeters, right? So then you could calculate the difference between here and here. And if we say that that difference is 65 millimeters, right? So then that means that if we have 760 millimeters of mercury, which is atmospheric pressure, that is the pressure that's represented by the atmosphere.
Okay.
And we subtract 65, that's going to give me my pressure that's inside the flask.
Okay.
Okay.
Okay. Okay.
So if we do a chemical reaction and the gas that's generated is greater than the atmosphere, this gas is going to push the mercury on this side, up this side of the column. So the difference between here and here, again, we're going to say it's 65 to keep it simple, right? That's going to just be added on because we know that this gas inside of here is greater than atmospheric pressure. That's why it's pushing the other way. So it's atmospheric pressure plus whatever distance that is, which is 65.
Okay.
Okay, does that make sense?
Yes, that makes sense now.
Okay. So the pressure inside a steam boiler is 1,427 psi's. Express this pressure in atmospheres. What am I going to do? Now, don't everybody yell at me at once. So much.
You start with your given of 1427 psi. Sorry, I was writing down the problem.
Okay.
And then
1 atom is equal to.
Yeah, you put 14.7 psi on the bottom and 1 atmosphere on top.
On top.
Okay. And that's going to equal
1427 divided by 97.
oops,
97.07. Can we say
97.07.
yes, can we say 97.1? Can we
Well,
write it?
it should be 4 sig figs, right?
Yeah.
Okay, give me 1 second, please. Okay. Okay, so the pressure in an automobile tire is 29 psi on a day. The weather report states the barometric pressure is 30.09 inches of mercury. How would you report the absolute pressure in the tire to a colleague in kilopascals? Okay, so what are we going to do?
Does the barometric pressure affect the PSI on the tire? Or are we just converting the PSI of the tire?
So think about it. We want the absolute pressure, right? So we're looking for absolute pressure, which means that it's going to be the combination of both the barometric pressure, which is just the atmospheric pressure.
So is it going to be 29 psi?
Okay.
Times.
So what are our conversions?
Pascal.
So
divided by 14.7?
We know that 1 atmosphere is equal to 14.7.
Mm-hmm.
We also know that 1 atmosphere is equal to 101.325 kilopascals, right?
Yes.
So then we could say 14.7 psi
Is equal to kilopascal.
is equal to, yeah. And we could say, because we'll need it later, getting ahead of the game here. 1 atmosphere is equal to 29.92 inches of mercury.
Yeah.
So then I can sit there and say that 29.92 inches of mercury is equal to 101.325 kPa. Okay. So then I can sit there and see if I can make this pretty. So we have 29 psi. So what do I need to do? Who's going to be on top and who's going to be on bottom?
101. It's going to be on top kPa, then 114.7 psi. So we can divide each other.
Yeah.
Can cancel each other rather. PSI and PSI can cancel each other. And that will give us the kPa.
That's going to get equal.
We calculate it. 29 divided into 29 times.
How many 6/8 should I have?
Two.
Okay. So then we need to do the same thing for the barometric pressure. So it's 3.3.
No, I got something else though. Oh, you ran it up, right? I got 1.99 something. So you rounded it up, right?
Oh.
Yeah, it should be
I
2.
got different thing. So it should be 2.
I screwed up, so it should be 2. Yes.
Okay.
My bad.
So we do the same thing for the other one too.
Yeah. So
Over 29.92 mercury.
that's
29.292 mercury. Multiply into 5 divided by 2.
So, and if we add those two together, we get 3.0 times 10 to the minus 2. I mean 10 to the 2, not minus 2. kPa. Let's do the plus here. So it doesn't look like Pat. There you go.
So, Doc, what I got here is different though. Here, I got 101.
You got 101?
Mm-hmm.
Okay, so I must have entered something wrong. Oh, I
I think
forgot
'cause
to
you did-
multiply. Yeah, I
you
forgot to
did
multiply
30
by. Yes. My
And
bad.
you did 30.03. It's 09.
Okay, so that's two things I did wrong.
Sorry, you can use your test correction for it.
All right. 101 point.
Oh, I wiped it off.
What?
Sorry, I cleaned it off. Let me
0.9.
quickly do it again. Yeah,
0.9.
0.9.
Okay. So here, when we add them together, 2 sig figs, 4 sig figs, so we end up with 2 sig figs. So it'll be 3.0 times 10 to the second power. Okay.
Oh, okay. Yeah, I see it.
No, I can't see yet.
Okay, so let me write it out. So this is here, this is 200, right? So that's 200, but this 0 is significant. So we're going to put a line over it to let us know that it's significant, or under it, whatever. So if this is significance, we draw that line, right? So then we end up with 300 with the line over the 0. So that I don't have to draw it with a line over a 0, and somebody just thinks I'm on crack, I just put 3.0 times 10 to the, because that's 2 sig figs right there. Do you see it, Rocky?
I'm trying to understand. Where did you get this 3.0 times? Yes, that one.
Okay, because I added the two together.
Oh, okay. Okay.
Okay. Clear. Come on. Okay, so we've already talked about the relationship between pressure and temperature, but there's also a relationship between volume and temperature. So as volume goes up, temperature is going to go up. Okay, and that's basically being shown here. And so in this case, we have height, because in the case of a thermometer, even though it's the volume, we're only looking at the height that's actually going up. Okay, because it's the volume of the column. So, and since in the thermometer, the area of the circle is going to be exactly the same, or the area of the column is going to be the same. Okay, so absolute temperature. Absolute temperature is I'm sorry, not absolute temperature. Absolute 0. Okay, absolute 0 is the temperature where you have 0 degrees Kelvin, which is equal to negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit. This temperature is the temperature where all motion stops. Everything stops moving at that point. So that's what the Kelvin scale is based upon. 0 is where you no longer have movement of molecules. Okay.
Mm-hmm.
Okay. So in the case of Charles's law, which is looking at volume and temperature, we've kind of already shown that volume is directly proportional to temperature. So we can make them equal to each other. Directly proportional doesn't mean equal, but by us putting a constant there, it allows that proportionality to become actual. So volume can equal a constant times temperature. You guys know what a constant is, right?
Mm.
If I say something is constant, what does that mean?
Mm.
That it's
Continuously?
continuous? Yeah.
Is it continuous?
Constant.
Something is constant.
It
It's
doesn't
constant.
change.
I mean regular. Is it regularly or something? I don't know how to say. Constant. Constant, like always or something.
So if I say my life is constant, what would that mean?
If you say your life is constant,
My life is constant. What would that mean?
I guess we don't know.
Okay. So constant means the same. It's not
the
changing.
same, yeah.
Yeah. Okay.
That's
So
a word.
something that isn't changing. So if you have a constant, a value that is constant, let's say 5, it's always going to be 5. It's never going to be anything else except 5. Okay. So that's what a constant is. So it's not going to change. So the relationship, if we have a fixed volume and a fixed, I'm sorry, not a fixed volume, a fixed pressure and a fixed amount, meaning that those things are not changing, they're the same, right? Then your volume and temperature are going to be constant. They're going to equal a constant. Okay, so the volume divided by temperature is going to equal a constant. Okay, so that value there is going to be exactly the same all the time. Okay, so then regardless of what volume and temperature I have, if I'm in this system, V1 over T1 is going to equal that constant. Then I can sit there and say, if I have a different volume and a different temperature, it's also going to equal that constant, right? So then I can sit there and say V1 over T1 is equal to that constant, which is equal to V2 over T2. So then I could just sit there and say V1 over T1 equals V2 over T2. Are you with me? So that's the significance of a constant, right? Do you guys get that so far?
Not really, though.
Okay, so let's say constant just means that it doesn't change, right?
Mhm,
It's a value that isn't going to change. So if it's 8, it's always going to be 8. So if it's 8, V1 over T1 is going to equal 8, right?
Mhm.
And then that also means that it never changes. That means V2 over T2 isn't going to change.
Okay.
Right? It's 8. Okay, so since they're both 8, can I just say V1 over T1 equals V2? Oops, not W. Come on. V2 over T2. Because it's 8, right? Isn't V1 over T1 8? And V2 over T2 8? So can't I just set them equal to each other?
No.
I can't?
I can't hear you. You're breaking.
I said I can't set them equal to each other? Can you hear me now?
I can hear you now.
You can hear me now?
Yes.
Okay, so I can set them equal to each other, right? So regardless of what V1 and T1, long as they're proportional, right? They're going to always equal 8. So that means V2 over T2 is always going to equal 8. So I can set V1 over T1 equal to V2 over T2.
Okay.
Okay, where T represents the temperature and V represents the volume.
Oh, okay.
Does that make sense? So a constant just means that it's the same number. It's not changing. It's always going to be a particular number. Okay. Is that good? We're good?
Yes, I'm good.
So a container with flexible walls holds a gas that is cooled from 65 degrees Celsius to 22 degrees Celsius with no change in temperature, no change in pressure, sorry. If the container volume is 4.5 liters initially, what will be the volume after it is cooled? So we're going to use this equation, right? So we have V1 over T1 equals V2 over T2. So our T1 is what?
T
65.
Is 65 degrees Celsius. Now, when we're working with gases, we always have to convert our Celsius to Kelvin.
Oh.
So we want to put this in Kelvin. So we add 273.
Mm-hmm.
And that's going to equal, what is that, 338 Kelvin?
Yeah.
So then our T2 is going to be
22 degrees
22 degrees, right?
Celsius.
Plus 273. So what is that? 295. And our V1 is what?
4.5.
Mm-hmm.
And our V2 is what we're looking for. Question mark. Okay, so let's solve for V2. So we get V2 is equal to V1 over T1 T2. So now it's just plug and chug. You know why it's called plug and chug?
So 44.4 liter. Oh, okay. So in the middle here, what's gonna be here though? Between the 4.5 liter and 2.95.
So what was your question? I'm sorry, Rocky.
My question is here, the 4.5 liter, you kind of written together. Is that how it's gonna be? Z plus or multiplication?
Oops, sorry. Did I screw that up? No, I got it right. So is it So T1. You said, is it multiplication? Yeah. So 4.5 liters times.
Okay.
Yes. Yeah. So it's understood if they're written like next to each other, it's fine.
Okay.
Yeah. So then that's 3.93.
We need just 2 sig figs.
Yep, you're right. So it's 3.9. Piece of cake?
Yeah.
Okay. Here.
Okay.
Or did I delete too fast? Everybody good?
Yes. Yeah? Yes.
Okay. Okay, so that was Charles's law. So now we're going to talk about Boyle's law. Boyle's law is looking at pressure and volume, right? So as pressure goes up, volume is going to go down. So they're indirectly proportional. Okay, so we can do exactly the same thing that we did with Charles's law. So here we have V is equal to a constant times 1 over the pressure. Then we could get pressure is equal pressure times volume is equal to a constant. And so we could say P1 V1 is equal to a constant. And then we could say P2 V2 is equal to a constant. And so we could set those guys equal to each other.
Pressure.
Okay. Are you with me, Rocky?
Yes, I'm with you, doctor.
Okay, I just want to be sure. Okay, so a gas sample occupies 5.818 liters at 776 torr. Find the volume of the gas if the pressure is changed to 827 torr. Temperature and amount remains constant. Okay, so we're going to be using that equation, right? P1 V1 equals P2 V2. So in this case, we don't have to convert torrs to ATM. We can leave it as torr, even though that ATM is typically, or pascals is SI units, but we typically use ATM, okay? We can leave it as torrs because those units are going to end up canceling each other out, okay? So our P1 is what?
776.
Torr. And our P2?
827.
827 torr. Our V1?
5.818 liter.
Our V2? is unknown,
That's
right?
what I'm looking for.
So we solve our equation for V2. Times, okay, that dot is an ugly dot. I'll just use an X. 5.18 liters divided by 827 torr. Okay, so our torrs are going to cancel out, and so we should just be left with liters. And what do we get?
4.86.
Okay, so we get B2 equals 4.86 liters. Simple.
Yeah.
So can I clear it?
Yeah. Well, I'm good.
Hold on, Doc. Don't click. Ah,
Oops. There you go.
thank you. V2. Thank you.
Let's see, clear. Z. Clear. Can't clear. Clear. Okay. Let's see. Okay. So we've talked about Charles's law. We've talked about Boyle's law. So we can actually combine both of those laws together, and then we get what we call the combined gas law. And this is kind of getting us almost to the point of the ideal gas law, which we'll be talking about here in a second. Now, the combined gas law allows us to sit there and say exactly the same thing. Here we have pressure times volume divided by temperature is going to equal to a constant. We say exactly the same thing, so we could say P1 over V1 over T1, sorry, P1 times V1 over T1 is equal to P2 times V2 over T2. Okay? So if we're given pressure, volume, temperature, and we're given temperature and pressure, then we should be able to calculate the volume, right?
Yeah.
Okay. So a cylinder in an automobile engine has a volume of 352 cubic centimeters. This engine takes in air at 21 degrees Celsius and 0.945 atm pressure. The compression stroke squeezes and heats this gas until the pressure is 4.95 atm and the temperature is 95 degrees Celsius. What is the final volume of the cylinder? Okay, what are we going to do?
We're going to start from giving, right?
Okay, so we have our givens. Write our givens out. I love that. So our V1 is what?
V1 is 21.
V1 is 21.
So hold on though.
It's 352.
352. V1 is the volume, right? So 352 cubic centimeters.
What am I looking at?
We're looking at the temperature.
Yes.
Our T1 is 21 degrees Celsius. So it's really important to pay attention to units here. So we need to change that to Kelvin. So we add 273. And so that gives us 294 Kelvin. Yay, nay, or may.
Yeah.
And our P1 P1 is what?
P1 is going to be 0.945.
Our P2
P2, that's the 65 degrees. Oh, you wrote it already.
Our P2 is 65 degrees.
Is that what I said? 65? 95, I mean, sorry.
Our P2, not our T2.
Oh. P2.
P as in pressure.
$4.95.
4.95 ATMs. And so it's important that we pay attention to our units because T is temperature, right? So we want to make sure that we're putting temperature, not pressure, right? Let me fix that real quick. So we had 95. Series C plus 273. So that's going to equal.
Though, can you move somewhere? It's not readable.
Okay, let me put it up here. Really small. T2. (95 degrees C plus 273. 368 Kelvin. Okay, so then we're going to use our equation, which is what?
P1 V1 over T1 equals P2 V2 over T2.
And we're solving for V2. So that's going to be P1 V1 over T1. Then you have P2 at the bottom and T2 at top. Then we got to plug all of that in. So we have P1, which is 0.945 ATM times 352 cubic centimeters times our T2, which is 300. I'm running out of room. Let me move everything over a little bit. This just happens to be in class a lot on the board. So our T2, which is 368 degrees Kelvin, divided by our T1, which is 294, times our P2, which is 4.95 ATM. So our ATMs are going to cancel. Our Kelvin's going to cancel. So we're just left with cubic centimeters. So we get, I have to put this up here, B2 is equal to what? How many sig figs should we have?
I'm sorry, God, but I thought I had did it wrong.
What was that?
That's what I got, but I thought I had done it wrong.
84.1?
Yeah.
That's correct. Are you with me, Rocky?
Yes, I'm with you, Doc. I'm trying to calculate up by input wrong numbers.
Okay. Yeah, it's a whole bunch of numbers, right?
Mm.
Okay, you guys ready to move forward?
Yeah, I got the same.
You got the same?
Yeah.
Okay, good. Okay, so let's move to the next one. Come on. Clear. Okay, STP. STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius, which is the same thing as 273 degrees Kelvin. And pressure, it's 1 bar. So it's really supposed to be 1 bar. However, a lot of times we will substitute 1 bar for 1 atmosphere. On the exam, if you're asked 1 bar or 1 atmosphere, put 1 bar. Okay, they're about the same because 1 bar is almost equal to 1 atmosphere. Okay, so now STP, I'm going to give you guys the ideal gas law. And this is kind of early, even though we're not going to use it immediately, but I want to give it to you so you know it. So put it up here. The ideal gas law is PV equals N RT. Okay, P, of course, equals pressure. V equals volume. N equals number of moles. R is the ideal gas constant. It's also called the universal gas constant. Of course, T is what?
Temperature.
Okay. So, molarity, I mean, not molarity. Molar mass is what? What is the units for molar mass?
Oh, damn, I forgot. For molar mass, is it AMU?
Everybody says that.
So, am I
So,
remembering wrong?
no. So, molar mass. Molar, what do you think molar stands for?
Referring to the mole.
Yeah, mole.
Okay, so molar mass. So how do we measure our mass? Molecular mass is AMU, or formula mass is AMU, right? So how do we measure our molar mass?
Would it be moles cubed?
It's not moles cubed. Molar mass. What is mass? What are the units? How do we measure mass? What units do we measure mass in, and what units does everybody else measure mass
in?
In
Kilograms?
gram and mole.
in kilograms or grams, right? So what was that? I heard somebody say it, grams per mole. So molar mass is grams per mole. We always do grams per mole. You should know that. I'm going to burn you now. I'm going to put that on the test. Okay, so molar mass is grams per mole. So if I want molar volume, what do you think that is?
Would that be liter?
Okay, liter, what? If molar mass was grams per mole, what do you think
Yes,
molar
liter per
volume is?
mole. Liter
Liters
per
per
mole.
mole, that's right, liters per mole. Okay, so if molar volume is liters per mole, so then that's volume over N, right? So if we solve PV equals nRT for V over N, we get RT over P. So if we calculate this for at STP, standard temperature and pressure, oh, let me give you the value of R. Let me move this over. Okay. R is going to be equal to 0.0821, and the units are ATM, liters over moles Kelvin. Okay, so then if we plug our units at STP, so R 0.0821 ATM per liter divided by moles Kelvin. Times T, which is 273 Kelvin. So that means Kelvin is canceling out with Kelvin. Divided by P, which is 1 atmosphere. Oops, totally missed that. Oops. Okay. So I should end up with 22.4 liters per mole. Okay, so regardless of what it is, anything, it could be oxygen, it could be carbon dioxide, it could be hydrogen, the molar volume at STP is always going to be exactly the same. It's going to be 22.4 liters per mole. Okay? Okay, keep that, plug that in the back of your mind somewhere. Can I erase it? Ready to move on?
Yeah.
Okay, good. Come on. Okay, so it says the volume of a sample of nitrogen gas is measured as 3.62 liters when it is at 0.843 bars at 16 degrees Celsius. What is the STP volume of nitrogen gas sample, of the nitrogen gas sample. So what equation are we going to use? So let's write down what we're given. What is our P1?
The 0.843 bar.
Equals 0.843 bars. Okay, what is our T1?
(16°C plus the 273, so 289 Kelvin.
What is our V1?
3.62.
What is our T2?
Would it be 0°C plus 273, so 273 Kelvin?
273 Kelvin. Our P2?
1 bar.
And we're looking for V2. So what equation are we going to use?
The combined gas law.
That's right. That's P1 V1 over T1 equals P2 V2 over T2, and we're solving for V2 again. Okay, so then we just plug and chug, right? Plug it in and we chug a beer. I need to move this over again. Keep running out of room. T2, 273. T1, 289. And P2 is 1 atmosphere. I mean, 1 bar, sorry. Okay, bars are going to cancel. Kelvin's going to cancel, and we're left with liters. What do you guys get?
Was it 2.88?
2.88. Piece of cake? Well, we lost everybody.
Yeah.
Started with 5, we're down to 2.
Didn't even notice they left. Must have had to eat dinner already.
Yeah. Okay. Are we good so far?
Yes.
Yeah.
Okay. So the Gay-Lussac is basically comparing pressure to temperature. So it's the same concept. So now we're able to do the same thing with pressure. We can say P is equal to a constant time temperature. And then we could go through that same process again. Okay. So Avogado's law compares volume to quantity, right? Or moles. And so it's the relationship of volume and moles. So they're directly proportional. So as the volume goes up, the number of moles are going to go up. And this is just basically showing you that. Okay. So now these are all of the different laws, right? So you have Charles's law, you have Boyle's law, you have the Gay-Lussac, and then you have the combined gas law. And then what they've done is basically they combined all the laws together to get the ideal gas law. Okay, so then the ideal gas law is PV equals nRT. I already told you about what the ideal gas constant was. I gave you the value for it. Now, it's only based upon those units. If you change those units, so if you have torrs, that constant is going to be different because you're using torrs instead of atmosphere. So you just need to multiply. You need to do the conversion to change atmospheres to torrs. So you'd multiply by 760 torrs to make it torrs. Okay. So that's why it's important to pay attention to the units. Okay, so the ideal gas law is PV equals nRT. That's what you need to tattoo on your chest. Okay. So if we sit there and pay attention to the ideal gas law, we can get to all of the other laws. So if we go with fixed volume, not fixed volume, fixed number of moles and temperature, we're going to get Boyle's law. If we go with fixed number of moles and pressure, we get Charles's law. If we go with fixed pressure and temperature, we get Avogado's law. So from there, you can derive all of the other laws. Are you with me?
Yeah.
And we're going to skip this because this is just calculating the universal gas law by manipulating PV equals nRT. You should be able to do that. Okay, so now we know that to calculate the number of moles is going to be mass divided by molar mass, right? Or M over Mn. So if we have mass divided by molar mass, we can substitute that into our equation for number of moles. And then so we get PV equals mass times the ideal gas law, T, over molar mass. Okay, so this is kind of cool because what is density? How do you calculate density?
DMV?
DMV, okay, that's true. DMV, so density. So if we use
Is equal to
density is equal to mass over volume.
Over volume.
Right? Right? DMV. Okay? So mass over volume. So we can calculate the density of a gas, right? So since we have mass now, so we use PV equals M over molar mass RT. So then we just solve for MV. And that's just going to be okay, so that'll be P times molar mass divided by RT. Okay, so the beauty of this, right? This simple equation, we can sit there and manipulate to sit there and calculate molar volume. We can calculate molarity, right? We can calculate, molar mass, molarity. We can calculate density. We can calculate molar mass. We can calculate, of course, you can calculate pressure, all those things as well too. Right? So by moving the equation around and knowing the definitions, it allows us some flexibility. Okay? We good?
Yeah.
You have that look, Jason. Are you tapping out on me? You can't tap out yet. We got another 30 minutes.
I'm multitasking here, but I'm paying attention. It's finals week. You know how it goes.
Oh, yeah. Okay, so what is the pressure, ATM, in a helium-filled 0.77 liter balloon if it contains 1.0 grams of gas at 22 degrees Celsius? What am I going to use? What equation? So what's given to me? So we have, what's this?
Volume of
Volume.
the balloon, which is
So that equals
0.77.
0.77 liters. What else is given?
The mass of 1 gram.
Mass. 1 gram. What else is given? Temperature.
And whenever we're doing these, we're always going to convert to Kelvin, right?
That's right.
Okay, so 295 Kelvin.
And we're looking for pressure. So what equation am I going to use?
Is it?
Is it PV equal to M over MM? Then RT.
So then we get P equal to
MRT, right?
RT over V, right?
Yes.
Okay, what is MM?
Molar mass.
Molar mass. So what is the molar mass of helium? Because it's a helium-filled balloon, right?
Mm-hmm.
It's in grams per mole. Is that what we said molar mass was, or am I forgetting already?
It's grams per mole, but what is it? What's
Okay.
the actual value?
So then it would be 4.
That's right. 4 grams per mole. And you got that from where?
Exactly. I want to know.
The
I
T
don't
table.
know. Oh, you look for helium, right?
That is correct.
Oh,
I think it's easy to forget the basics.
yes,
Uh-huh.
yes.
I do that in calculus too.
Okay, so we just plug in our values, 1.0 grams. You guys aren't going to hate me if I don't put in all of the units for R, right? Or will you hate me?
I don't know. No.
Let me see. I can get them in here. I just got to move stuff around. Hold on. Give me a second. I got to pull this way over here. So we know that R is 0.0821 ATM. ATM.
Oh, can't you just write 22.4?
Is it at STP?
Oh, it's not. Never mind.
Yeah. And so that's ATM per moles Kelvin. Times RT. RT is 295 Kelvin. Divided by 4 grams per mole. Times our volume, which is 0.77 liters. Okay, so then liters are going to cancel out. Kelvin is going to cancel out. Moles are going to cancel out. Grams are going to cancel out. And so we're just left with ATM. So we get P equals so how many stick tapes should I have?
I want to say 2.
That's right, 2.
Was that because our grams was the lowest?
Yep, we had 2 here, we had 2 here. So both cases we had 2.
Okay.
Okay, piece of cake.
Mm-hmm.
Okay, good.
don't you raise the chat, dog, please?
Okay, I won't.
Isn't this also a lot of the stuff you're going to do in physics too?
Yeah, you do some of this in physics, yes. Yeah, you talk a lot about pressure and force. Are you ready, Rocky? Let me know
Yes,
when
I
you're
am
ready.
ready. I am ready.
Okay, so now I can clear. Okay, so we can calculate density. We've talked about that already. I already showed you how to get there. So we can sit there and solve the equation for density in this case. So what equation are we going to use, Rocky or Jason?
Is it going to be PV equal to M over molar mass?
That's right. And then we're solving for density. So then it's going to be P times molar mass over RT equal to M over V. So we're going to change our pressure to atmospheres. So P is going to equal to 744 torrs. How do I change that to atmospheres? How many torrs or how many atmospheres? How many torrs equal 1 atmosphere?
760.
Okay. So I have 1 atmosphere on top. 760 torrs on the bottom. So then we get P equals, what is that? 9 something, 0.9 something, or
0.979. Would we go
366? That's right. So 0.979 ATM. Okay, so then we can plug that in there. And we're working with what? Helium? What is the molar mass of helium?
More.
Okay, so we have 0.979 ATM and 4 grams per mole. Divided by 0.0821 ATM liters moles Kelvin times temperature is 22. So 22 plus 273. So that's 295 Kelvin. So then Kelvin cancels out. ATM cancels out. Moles cancel out. And so we're just left with grams per liter. So
Would it be 0.162?
you said 0.162
Yeah.
grams per liter. Okay, piece of cake.
Yeah.
Okay, so I have one thing more that I want to go over. So we've already talked about molar volume. right? And their calculation is 22.7 instead of 22.4. You can use either one. 22.4 is because that ATM, an ATM is really a 1.013. So if you do that math, it'll give you your 22.7. But I'm not gonna dock you too much. And it's all multiple guess, so all you're gonna do is multiple guess it. So you guys can do this on your own. All the notes are available to download anyway, so you know.
Notes.
Okay. What was that?
You said all the notes are there to be down. Okay.
Yeah, you can download the notes. Yeah.
You made the slides?
The slides, yes.
Okay.
Yeah. Okay. So because we're working with chemistry, we can also do reactions, and some of our reaction produces gases. So we can use stoichiometry to sit there and calculate how much gas is being generated, right? So that's going to give us a number of moles of gas. It can also give us our mass of gas. But we can use that to calculate our volume or our pressure that the gas is going to be generating, or the temperature of the reaction, depending on what's going on under the circumstances. You guys get that?
Nope.
You said
Sorry.
nope?
Yes, though. I don't know. I don't get it.
You know you didn't get it?
I didn't get it, please. Sorry.
Okay, so I'll repeat it again. Because we're working in chemistry, this stoichiometry is going to apply to this as well.
Oh, okay.
We do reactions all the time where we're producing gases. Do you guys remember how much gas did you guys produce when you did the balloon? Right? Wasn't gas being produced?
Yes.
Yeah.
So we can actually calculate the volume by using the ideal gas law of how much gas we should be calculating based upon the chemical components, right? Yeah, no, maybe.
Right.
Okay.
Yeah.
So we can sit there and use that to sit there and calculate our volume, and then we can compare that volume to what we actually got. Is that true? True or false? Yeah, no, maybe.
Yeah.
Okay. So, sorry.
I feel
We're in the last few slides. We're almost golden. This is the last major thing I want to show you. Okay. So here we have the volume of hydrogen gas is measured at STP. Oh, so I'm sorry. What volume of a hydrogen measured at STP can be released by 42.7 grams of zinc as it reacts with hydrochloric acid. So here we're doing a chemical reaction and we're releasing a hydrogen gas. Okay, so is our equation balanced?
yeah.
So now that we know that our equation is balanced, what are we going to do? So if we want to calculate how much gas we're making, what are we going to do?
Are we starting with the given?
We're starting with our given. Okay, so our given is 42.7 grams of zinc.
So that means we have to look for molar mass of zinc, right?
Okay, so what is the molar mass of zinc?
Let me quickly check it. $65.38 grams.
Grams per mole, right? Okay, so grams are going to cancel out. Then what are we going to do?
Here we are doing. So 1 mole of zinc will be at the bottom. One mole of hydrogen. We have to look for.
Okay. So we do the math.
So 0.653.
Come on. 3 moles of H2. Okay, so now what was that number that we got for molar volume at STP? Because isn't this at STP?
Yeah, we had 22.4.
Okay, so if I have 0.653 moles of H2, and you said it was 22.7 or 22.4, depending on which one you use. So it's 22.4.
So we could use either 27.7 or 0.4.
You can use either one. 22.4 is going to give you roughly the right answer. 22.7 is going to give you roughly the right answer. Oops. And sorry, that's liters per mole. I screwed up. So then that means that this cancels out. Right? And then you're left with, what do you get?
14.6.
0.653 times
14.6 liters, right?
Yep.
Of H2. Okay, that's the quick way of doing it. Now let me show you the long way of doing it. So now we have the number of moles. So this is equal to N, right? So we can use PV equals nRT. And then we solve for V. So then we get V equals nRT over P. Okay, so then we get V is equal to, and we just plug in our values. That's 0.653 moles. We have R, which is 0.0821. And then we have our temperature, which is at STP 273. 270. Oh, I'm running out of room badly. I'm going to move this down and over. This guy down. And move this guy over. I messed up line there. ATM. Oops. Running out of room again. Hold on. Fix this right. Come on. ATM. Liters over moles Kelvin, need more line, times 273 Kelvin all over our pressure, which is 1 ATM. And so you should end up with approximately the same value of 14.6 liters of H2. Okay, piece of cake.
Yeah.
Okay, I'll let you guys copy that down.
Please don't raise it yet, please.
What was that?
Okay.
Yeah, so there's two different ways of getting the same answer.
Oh, this is another way to get the answer, right? Oh,
Yep. Yep.
Oh, I see. Let me write it down, please.
Yeah. So the molar volume is a nice way of doing it if it's at STP.
You are so tired.
It's been a long day. I still have to drive an hour and 15 minutes.
So where's West Hills at?
So we have 3 campuses. Well, we have 2 campuses and a satellite. So I'm at what used to be the main campus, but now the main campus is really Lemoore. So although we're technically a main campus too, but Lemoore is a much bigger campus. It's like a real college there. Ours is kind of like a old high school, little high school in Kalinga. Okay, so I'm the instructor for Kalinga. There's another instructor at Lemoore for chemistry. And so here, I teach here and I teach at Fireball. Fireball is a center, but they're building a real big campus and they're going to eventually make it a campus. But here, we are located between, so you're near 101. You guys are kind of, well, not near. You got 1. I think you guys are closer to 1 than 101. But
no, we're basically on 101.
Okay, so we're about an hour and 50 minutes away from where you guys are located at. That's where Kalinga's at. Now, from Kalinga to where I live in Hanford, it's about an hour 10, hour 15, depending on how traffic is and how many police are out. And from Kalinga to Fireball, so I teach at both Fireball and Kalinga. So depending on the day, I'm at either one. They used to, the guy that used to do scheduling before, I think he wanted to try to get me to quit. So he would put them on the same day. So I was driving.
Wow, back and forth.
Hour and 30 minutes, yeah, from one campus to the other campus. Yeah. There's one semester, I would start in the morning in Kalinga. I would go to Fireball midday, and then I'd come back to Kalinga. And then I'd have to drive to Hanford. Yeah, it was crazy.
You don't have family in any of those towns? Just stay with them.
What was that?
So you don't have family in any of those towns? Just stay with them?
I had no family in either of those towns. Yeah, nope.
Dang.
And so, yeah, it was a commute. Yeah, he did that to me my very first, when I officially got hired. And he didn't really want me to get hired, so he had a friend that he wanted to get the position to. So he was doing his best to get me fired or get me to quit, one or the other.
Oh, sorry. This 0.0821, is that R?
That's R.
Okay.
and R is a constant. So it's always going to be the same, long as you use the right units, you know. So you always want to have ATM. Anytime that you're using R, you want to make sure you have ATM, liters, and Kelvin.
Okay.
My watch tells me to breathe. It says breathe.
Well, yeah,
So-
you're over here chugging coffee at like 8 p.m.
Yeah. Well, I need to drive home, so I was like, I need to make sure I stay up.
Doc, so on the exam, are you going to give us calculation like this or no?
Of course.
Okay.
You're going to have a couple of those. Okay. Let's see. So that was the last thing I wanted to talk to you about. And if you look at the notes, there's a couple of other problems, and I don't know what the hell's going on with my notes. They're all screwed up. The arrows are all shifted. So there's a couple of other examples. I think there's 2 other examples that'll take you through it. So you guys can do that on your own. It's pretty simple. As the tire pressure gauge reads 33 pounds per square inch. So 33 PSI. How many kilopascals is this?
Kilopascals.
Yeah. Remember that multiply steps may be required in the conversion. Okay. So if we're talking about the pressure gauge, so that means the pressure of the tire plus the pressure of the atmosphere, or atmospheric pressure. So what is the conversion for PSI to kilopascals? You know, I'm looking at this and
All right, I'm gonna go because I haven't had dinner yet. I'll see you on Monday.
okay, sounds good.
All right, enjoy your weekend. Ronki, I'll talk to you in the group chat, probably.
Yes, we will. We sure.
Yeah.
Thank
Okay.
Thank,
See you guys
thank
later.
you. So I'll
Okay.
see you later.
Okay, Ronki, this is what you're going to do, right? You got what I'm talking about? You understand it? Oops. Did I not share? Am I not sharing my screen?
Let me stop sharing, right?
Okay. Yeah, you start sharing. Can you see my screen?
Yes, I can.
Oh, wrong screen now. Oh yeah, no, right screen. Okay.
It's yours.
Okay, so that's the question, right? So remember, in this case, it's going to be, this is what you read for your gauge pressure, right? It says the tire gauge is this. Okay, how many kilopascals is this? Okay, so if it's 33 PSI, then you want to convert that to, you want to convert PSI to, let's see, hold on. Okay, so you want to start with your PSI, right? And you can actually, it doesn't have to be multiple steps. All right, so let's see. I can't see all my thing at the bottom. Let's see if I can fix this so I can see the bottom. There you go. Okay, so then we know that 1 PSI, PSI 14.7 PSI Where are my units? There we go. Is equal to, where is my pKa? And that's it. So it's just like the example that we did earlier.
So that means it's going to be 22, 227.
Yep. That's it. Piece of cake?
It's okay.
Oh, they